let's start. Before we dive in, if you're fascinated by prehistoric giants, ancient mysteries, and incredible true stories backed by science, make sure to hit subscribe. We upload documentaries like this every week, and you won't want to miss what's coming next. Number 1. Megalodon. The year is 1835. You're Louis Agassiz, a Swiss naturalist working through a private fossil collection, and you are holding a tooth the size of your hand. It is triangular, serrated along both edges, enamel still dark and glassy after tens of millions of years underground. You have seen shark teeth before. You have never seen one this large. You classify it and give it a name built from two Greek roots, Megalodon, big tooth. You do not yet know what animal it belonged to, only that whatever grew this tooth was not something you would want in open water with you. The teeth kept surfacing for the next century. Quarries in the American South, riverbeds in Peru, the chalk cliffs of England, fishing nets off the coast of Japan. Each tooth told the same story in a different location. A predator distributed across every ocean on Earth, present for roughly 20 million years, from around 23 million years ago to approximately 3.6 million years ago. That is not a brief evolutionary experiment. That is one of the longest reigns of any apex predator in the fossil record. Nobody has ever found a complete megalodon skeleton, and there is a specific reason for that. Sharks do not have bone in the way mammals do. Their skeletons are cartilage, and cartilage almost never survives fossilization. What survives is calcified vertebral centra and teeth, because enamel is the hardest substance a shark's body produces. Everything paleontologists know about megalodon's size, they have had to reconstruct from those two categories of evidence alone. The reconstruction methods themselves have been a source of genuine scientific argument for decades. Early 20th century researchers scaled up the jaw using tooth size and modern great white proportions and arrived at estimates north of 100 feet. That number is wrong, and modern paleontologists know exactly why. Great white sharks are not built the same way Megalodon was. Its teeth are broader relative to its jaw, its body proportions likely closer to a modern mako or a lamniform ancestor than to a great white. A 2021 study published in Scientific Reports, led by paleobiologist Jack Cooper at Swansea University, used a more careful method, digitally modeling the whole body from partial vertebral columns and a broader dataset of living lamniform sharks. Their estimate, approximately 52 feet, roughly 3 school buses end to end, with a body mass exceeding 50 tons. The bite force calculation is where the science gets specific enough to feel less like paleontology and more like forensics. A 2008 study out of the University of New South Wales, using a digitally reconstructed jaw and finite element analysis, the same modeling technique engineers used to test how bridges fail under load, estimated Megalodon's bite force at between 108,000 and 182,000 newtons. For comparison, a modern great white bites at roughly 18,000 newtons. A saltwater crocodile, the hardest biting living animal, manages around 16,000. Megalodon's bite force estimate is not close to any living animals. It is not meant to be close. Nothing alive today evolved to fill the ecological role Megalodon occupied. What it ate is recorded directly on the bones of its prey. Fossil whale vertebrae recovered from Miocene-era marine deposits carry bite marks, punctures and gouges matching the serration spacing of Megalodon teeth. Some of them healed over, meaning the whale survived the attack, some of them not. A study of fossil whale bones from Sharktooth Hill in California found bite damage consistent with Megalodon on a significant percentage of specimens examined. This was not an animal that scavenged occasionally. This was an animal whose primary food source was baleen and toothed whales, hunted at a scale that shaped how those whale populations evolved their own defenses in response. The extinction date is where the story turns from monster movie into something colder. A 2022 study published in Nature Communications, led by Kenshu Shimada at DePaul University, using zinc isotope analysis of fossil teeth, placed Megalodon's position at the very top of the ancient food chain, a trophic level higher than any modern marine predator, including modern orcas. The same broad body of research points toward a specific culprit in its decline: the rise of the modern great white shark and other emerging apex predators competing for the same prey base during a period of global ocean cooling and changing sea levels roughly 3.6 million years ago. Not a single catastrophe, a slow squeeze, a smaller, faster, more efficient competitor arriving in the same waters at the moment Megalodon's environment was already narrowing. There is no mystery about whether Megalodon is extinct. The fossil record simply stops. No confirmed tooth younger than roughly 3.6 million years has ever been found, despite exhaustive searching in every ocean basin where older specimens turn up constantly. What remains is the scale of what was lost. A predator that patrolled every ocean on the planet for 20 million years, whose bite force still exceeds anything alive today, reduced now to teeth in drawers in museums from Charleston to Tokyo, each one a fragment of an animal too large for any single fossil to fully explain. Number 2. Mosasaurus. The year is 1770. You're a quarry worker in the limestone tunnels beneath St. Peter's Mountain, just outside the Dutch city of Maastricht. The limestone here is soft enough to cut by hand, and it has been mined for building stone since Roman times. Today your pick strikes something that is not stone. A jaw, enormous, studded with conical teeth, embedded in rock that has not seen daylight in roughly 66 million years. The skull eventually makes its way to a local surgeon and fossil collector named Johann Leonard Hoffmann, who spends years trying to understand what he is looking at. Nobody in 1770s Europe has a working framework for extinction. The dominant scientific assumption is that species do not disappear, that whatever this jaw belonged to must still be alive somewhere in an unexplored ocean. The specimen becomes locally famous as the great animal of Maastricht, long before anyone can tell you what kind of animal it actually was. The scientific resolution takes decades and involves two of the most important naturalists of the era. Georges Cuvier, the French anatomist, widely credited as the founder of comparative anatomy, and one of the first scientists to argue seriously for the reality of extinction, examines casts of the skull in the 1790s and concludes it belonged to a giant marine lizard unlike anything alive today. In 1808, as French revolutionary forces occupy Maastricht, the specimen is seized and transported to Paris, where it remains at the Muséum National d'Histoire Naturelle. The formal genus name, Mosasaurus, meaning lizard of the Meuse River, is assigned in 1822 by the British geologist William Daniel Conybeare, honoring the river that runs past the quarry where it was found. What the fossil record has since confirmed is that Mosasaurus was not an isolated oddity. It belonged to an entire family, the mosasaurs, that radiated explosively during the final 20 million years of the Cretaceous period, filling ocean predator niches vacated by other extinct marine reptiles. Genetic and anatomical analysis places mosasaurs as close relatives of modern monitor lizards and snakes, not distant reptilian cousins, but part of the same lineage. Adapted from land-dwelling ancestors into fully marine predators with paddle-like limbs and a long, muscular, laterally flattened tail, built for propulsion, klimt or near-complete Mosasaurus hoffmanni specimens, the species named for the collector who first tried to understand the Maastricht jaw, put the animal's length at approximately 50 feet, among the largest of all mosasaur species discovered to date. The skull alone, based on the original Maastricht specimen and subsequent finds, measures over 4 feet long, with a double row of hinged teeth on the roof of the mouth, in addition to the main jaw, an adaptation shared with modern snakes that let it grip and swallow struggling prey without releasing its bite. Stomach content fossils and bite-marked prey specimens tell a specific story about what filled that mouth. For ammonites with puncture patterns matching mosasaur tooth spacing, fish vertebrae swallowed whole, fossilized remains of smaller marine reptiles, including other mosasaurs, showing this was an animal capable of preying on members of its own family. A 2020 biomechanical study modeling mosasaur jaw musculature estimated bite forces for large Mosasaurus specimens in a range capable of shattering the shells of the largest nuts known from the period, closing a long-standing question about how anything could crack armor that thick. The end came with the same event that ended the age of dinosaurs. The Cretaceous-Paleogene boundary, dated with high precision to 66 million years ago through iridium layer analysis, first identified by Walter and Luis Alvarez in 1980, marks the point where Mosasaurus and every other mosasaur species vanish from the fossil record in the same geological instant as the non-avian dinosaurs on land. The asteroid impact that ended one age ended this one too, and the quarry beneath St. Peter's Mountain holds the proof. A jaw waiting 66 million years in the dark for a pickaxe that had no idea what it was about to find. Number 3. Liopleurodon. The year is 1873. Your Henri-Émile Sauvage, a French paleontologist working through fragmentary marine reptile, remains recovered from Jurassic clay deposits, and the material in front of you is frustratingly incomplete. Isolated teeth, conical, triple-keeled, unlike anything you have cataloged from other known marine reptiles of the period. You assign a new genus, Liopleurodon, smooth-sided teeth, based on the distinct ridge pattern. For over a century after that, this is essentially all science has to work with. Teeth and speculation. Liopleurodon belongs to a group called Pliosaurus, short-necked plesiosaurs with massive skulls and 4 powerful flippers. Built less like the long-necked plesiosaur silhouette most people picture, and more like a torpedo with a mouth. Better fossil material, recovered through the 20th and early 21st centuries, from Oxford clay formations in England and equivalent Jurassic deposits in France, has allowed more confident reconstruction. Adult Liopleurodon specimens are now reasonably well estimated, at somewhere between 16 and 23 feet in length, formidable, genuinely dangerous. An apex predator of the Middle Jurassic seas roughly 160 million years ago. That number needs to be stated clearly, because Liopleurodon is the case study in this list, where the popular imagination and the fossil evidence diverged hardest, and the divergence has a specific, documented source. In 1999, the BBC aired Walking with Dinosaurs, a landmark documentary series that dramatized prehistoric life with then groundbreaking CGI. One episode featured a Liopleurodon, described as reaching 82 feet in length and weighing 150 tons, roughly the size of a blue whale, presented with the same authoritative narration style used for well-supported paleontological facts. Throughout the series, the number did not come from a fossil. It came from a since-disputed partial jaw fragment found in Mexico decades earlier, scaled up using proportional assumptions that later specialists considered deeply flawed. And the production combined that shaky extrapolation with dramatic license for television. The 82-foot figure spread through the 2000s in encyclopedias, toy packaging, and children's books faster than any correction could follow it, becoming for an entire generation the default answer to how big was Liopleurodon, despite never having been supported by peer-reviewed skeletal evidence. Paleontologists have spent years since correcting the record. Richard Forrest, a British researcher specializing in Jurassic marine reptiles, who consulted on some of that era's documentaries, has been publicly explicit that the 82-foot figure was never scientifically justified and does not match any known specimen. The actual fossil evidence, complete skulls, and partial postcranial material from Oxford clay sites supports an animal in the 16 to 23-foot range, still one of the larger marine predators of its specific time and place, but not remotely close to blue whale scale. What the corrected size does not diminish is the bite. Liopleurodon's skull, based on the best preserved specimens, measures over 5 feet long on its own, proportionally enormous relative to body length, even at the smaller, evidence-supported size. Its nostrils were positioned to function less for breathing air, which it still needed to do at the surface, and more as a directional smelling apparatus underwater, allowing it to track prey by scent through water in a manner closer to a shark than a typical reptile. Stomach contents and tooth-marked bone from associated Oxford clay fossils show a diet of fish, ammonites, and other marine reptiles, consistent with an apex predator hunting near the top of a complex Jurassic marine food web. The correction matters because it is a rare case in paleontology where you can trace, almost year by year, how a single television broadcast outran the fossil evidence and then took 2 decades to be pulled back toward it. The real Liopleurodon was still one of the most dangerous animals in its ocean. It simply never needed to be a fictional blue whale to earn that reputation. Number 4. Kronosaurus. The year is 1899. You're a grazier in central western Queensland, Australia, working land near the town of Hughenden, and you notice something protruding from an eroded creek bank, bone, clearly, but on a scale that does not match anything you associate with local wildlife, living or extinct. Word travels slowly in this part of Queensland at the turn of the century, and it will be another 25 years before the material receives a formal scientific name. In 1924, Heber Longman, director of the Queensland Museum, formally describes the genus based on fragmentary remains recovered from the region and names it Kronosaurus after Kronos, the Greek titan who devoured his own children, a reference to the animal's evident predatory scale rather than any specific behavioral evidence. For the next several years, Kronosaurus exists in the scientific record largely as a name attached to incomplete bones, a predator known to have existed without anyone having assembled what it actually looked like. That changes in 1931, when a Harvard Museum of Comparative Zoology expedition led by paleontologist William Sheville, working a station property near Hughenden called Army Downs, excavates a far more complete skeleton over the course of a grueling multi-week dig in remote outback conditions. The specimen is shipped back to Harvard, and this is where the story becomes an unusually well-documented case study in the gap between fossil evidence and museum presentation. The Harvard specimen sat largely unprepared and unmounted in storage for over 2 decades. When it was finally reconstructed for public display in 1959, technicians filled substantial gaps in the incomplete skeleton with plaster, and later analysis by paleontologist Colin McHenry, who studied the specimen closely in the early 2000s, determined that the reconstruction had added an estimated 20% extra length to the neck region that was never actually recovered in fossil form, inflating the mounted skeleton's total length beyond what the physical bones alone support. McHenry's reanalysis, published in the mid-2000s, produced a corrected estimate of approximately 30 to 33 feet for Kronosaurus queenslandicus, still an immense predator, but meaningfully smaller than the traditionally cited 40-plus foot figure that had circulated in textbooks for decades based on the Harvard Mount's inflated proportions. The skull itself needs no exaggeration to be remarkable. Recovered material puts it at roughly 9 feet long on its own, among the largest Pliosaurus skulls ever documented, lined with conical teeth up to a foot in length designed for gripping and crushing rather than slicing. Kronosaurus inhabited the shallow inland sea that covered much of central Australia during the early Cretaceous, roughly 100 to 125 million years ago, a body of water paleontologists now call the Eromanga Sea, sharing that environment with long-necked plesiosaurs, giant fish, and early ichthyosaur lineages, all of which appear in the local fossil record, with bite damage patterns consistent with Kronosaurus predation. Additional specimens recovered from Queensland's opalized fossil beds near Richmond and Boulia through the late 20th and early 21st centuries, some of them preserved in opal itself, a geological process unique to this region, have continued to refine the picture without changing the central fact. Kronosaurus was real. It was one of the largest marine predators of the early Cretaceous, and its true dimensions were sitting quietly correct in the ground the entire time a plaster reconstruction was telling museum visitors something slightly different for over 40 years. Number 5. Shonisaurus. The year is 1928. Your Seaman Mueller, a geologist mapping rock formations in the Shoshone Mountains of central Nevada, in a stretch of high desert canyon that will later be named West Union Canyon. Scattered across the exposed rock are what look, at first glance, like enormous fossilized vertebrae, dozens of them, weathering out of the same limestone bed across a wide area. You are looking at what will turn out to be one of the densest concentrations of giant marine reptile remains ever found on the North American continent, and almost nobody outside a small circle of geologists knows it exists yet. Formal paleontological excavation does not begin in earnest until 1954, and even then progress is slow, the site remote, the fossils embedded in hard rock at high elevation with limited road access. Over subsequent decades of careful excavation, researchers document at least 37 individual ichthyosaur skeletons at the site, a density and concentration that eventually leads to the area's designation as Berlin Ichthyosaur State Park, and to the ichthyosaur being named Nevada's official state fossil in 1977. Shonisaurus popularis, the species formally described from the Nevada site, represents one of the largest ichthyosaurs known from North America. Estimated at up to 50 feet in length, based on the more complete specimens recovered. Ichthyosaurs as a group are marine reptiles that evolved a body plan strikingly convergent with modern dolphins and whales, despite no close evolutionary relationship. Streamlined, finned, adapted for sustained high-speed swimming through open ocean, having returned to the sea from land-dwelling ancestors roughly 250 million years ago, tens of millions of years before either Mosasaurus or Plesiosaurs made the same transition. The genuinely largest confirmed ichthyosaur did not come from Nevada, though. In 2004, paleontologist Elizabeth Nichols, working a remote site in the Sakoney Chief River region of British Columbia, Canada, recovered a partial skeleton representing an animal she and colleagues formally described in 2004 as a new species, Shonisaurus sakoniensis, later assigned by some researchers to a related genus, Shastasaurus. Based on the recovered skull and forefin proportions scaled against more complete related specimens, Nichols estimated a total length of approximately 69 feet, which would place it among the largest marine animals of any kind, reptile or mammal, ever to have existed on Earth, rivaling modern blue whales in scale, despite living roughly 210 million years earlier. What makes the Nevada bone bed additional scientifically important is the mystery it still has not fully resolved. The 37-plus individuals at the Berlin site died and were preserved together in a way that has prompted decades of competing hypotheses: a mass stranding event, a toxic algal bloom, a low-oxygen dead zone in ancient ocean water. A 2011 study, led by paleontologist Mark McMenamin, examining the arrangement of vertebrae at the site, proposed a more speculative interpretation, that the bones showed patterns suggesting deliberate arrangement, and floated the idea that a giant predator, possibly a colossal cephalopod, might have arranged them. That specific hypothesis has not been accepted by the broader paleontological community and remains a minority position. But the underlying puzzle it was trying to explain, why so many enormous ichthyosaurs died together in the same location, has never been definitively resolved through peer-reviewed consensus. What is not in dispute is the base fact of scale. An animal-reptile lineage that abandoned land for open ocean 250 million years ago produced, at its evolutionary peak, individuals rivaling the largest whales alive today, and the Nevada desert, one of the least likely places on the modern map to find evidence of ancient sea life, holds one of the largest concentrations of proof anywhere on the planet. Number 6, Elasmosaurus. The year is 1868. Your Edward Drinker Cope, a young, brilliant, and famously combative American paleontologist, and you have just received a partial skeleton recovered from Cretaceous chalk deposits in western Kansas, a region that 80 million years ago sat beneath the western interior seaway, a shallow ocean that once split the North American continent in two. The specimen includes an extraordinarily long series of vertebrae, more than 70 of them, the longest such series ever documented in a reptile at the time. Working quickly, in the competitive scientific climate of the era, Cope assembles and describes the skeleton, publishing his reconstruction with the skull placed at the end of the short segment of vertebrae and the extraordinarily long series extending out as the tail. He names the animal Elasmosaurus platurus. It is, by the standards of 1868 paleontology, a triumphant discovery, a plesiosaur unlike any previously known, with a body plan more extreme than anything yet documented. It is also wrong, and the correction becomes one of the most famous episodes in the history of American paleontology. Othniel Charles Marsh, a rival paleontologist at Yale and Cope's soon-to-be lifelong professional enemy, examines the reconstruction and identifies the error. The long series of more than 70 vertebrae is not the tail, it is the neck. Cope had put the skull on the wrong end of the animal. The mistake is understandable, given the anatomy involved. Elasmosaurus represents the most extreme expression of the long-necked plesiosaur body plan ever documented. A neck built from more cervical vertebrae than any other known vertebrate, longer than the animal's body and tail combined. Nothing in the existing fossil record at the time prepared Cope for a neck of that proportion, and his instinct to interpret the elongated series as a tail was, if wrong, at least a reasonable mistake given what science understood about plesiosaur anatomy in 1868. The public correction was not gentle. Marsh's identification of the error, and the manner in which it circulated through the tight-knit American scientific community of the era is widely credited by historians as one of the sparking incidents of what later became known as the Bone Wars, a decades-long, increasingly bitter rivalry between Cope and Marsh that drove both men to fund increasingly reckless fossil hunting expeditions across the American West, resulting in both extraordinary scientific discovery and, at times, outright destruction of fossil sites each man raced to exploit before the other could reach them. Corrected and properly understood, Elasmosaurus measured approximately 34 to 46 feet in length, with that neck alone accounting for more than half the animal's total body length, supported by 71 to 76 cervical vertebrae depending on the specimen, a number that remains, to this day, the highest vertebral count documented in the neck of any known vertebrate animal, living or extinct. The skull, by contrast, was small and narrow, lined with thin interlocking teeth suited to catching fish rather than crushing armored prey, and the animal is generally reconstructed as a relatively slow-moving ambush hunter, using that extraordinary neck to reach into schools of fish from a distance, without the rest of its large body needing to close in and spook them. Biomechanical studies conducted in the decades since, using computer modeling of the neck's articulation, have concluded the neck was likely far less flexible than early artistic reconstructions assumed, unable to bend into the swan-like curves popular in vintage illustrations, limited instead to more modest lateral and vertical movement. The animal's actual hunting posture was almost certainly less dramatic than its anatomy initially suggested, and more efficient because of it. Number 7. Dunkleosteus. The year is 1956. You're a researcher at the Cleveland Museum of Natural History, working through fossil material recovered from the black shale exposures along Lake Erie's shoreline, a formation that has been yielding fragments of armored prehistoric fish for over a century, since the mid-1800s, without any single specimens having been comprehensively studied and formally described. You finalize the description of a genus based on that accumulated material and name it Dunkleosteus, honoring David Dunkel, the museum's curator of vertebrate paleontology, who had spent years working with the Cleveland shale material. Dunkleosteus belongs to a group called placoderms, armored-jawed fish, that represent some of the earliest vertebrates to develop true jaws at all, a group that dominated the world's oceans during the Devonian period, roughly 358 to 382 million years ago, a span of Earth's history sometimes called the Age of Fishes. Unlike sharks or bony fish, placoderms did not have teeth in the conventional sense. Dunkleosteus's mouth was instead lined with sharp, self-sharpening bony plates that functioned as a shearing blade, growing continuously and wearing against each other in a way that kept the cutting edge perpetually honed. Complete Dunkleosteus specimens are rare, the Cleveland shale preserving the heavily armored head and thorax far more reliably than the softer cartilaginous rear portion of the body, which means total length estimates have shifted over time as reconstruction methods improved. Older estimates place the animal at up to 33 feet. A 2023 reassessment led by Russell Engelman, a paleontologist affiliated with Case Western Reserve University, used more rigorous proportional comparison against better preserved relatives and revised that figure downward to a more conservative estimate of approximately 13 to 14 feet for typical adult specimens. Still an enormous predator for the Devonian seas, but a meaningful correction from the earlier, less rigorously supported numbers. What is held up under scrutiny and been studied with genuine biomechanical precision is the bite. A 2006 study led by Philip Anderson and Mark Westneat at the University of Chicago and the Field Museum built a detailed mechanical model of the Dunkleosteus skull, incorporating a 4-bar linkage system in the jaw joint that let the animal open its mouth with unusual speed in as little as 20 milliseconds, generating powerful suction that pulled prey inward as the jaws closed. Their calculation placed Dunkleosteus's bite force at the tip of bony blades at approximately 8,000 pounds per square inch, among the strongest bite forces calculated for any fish, living or extinct, rivaling estimates for large modern crocodilians, despite Dunkleosteus predating the first true reptiles by tens of millions of years. Fossil evidence of that bite in action exists directly in the Cleveland shale record. specimens have been recovered, showing partially digested and regurgitated Dunkleosteus material, bearing evidence of cannibalism, animals preying on smaller members of their own species, alongside crushed and punctured armor, plating from other placoderms, and early sharks, consistent with the shearing bite mechanics the biomechanical modeling predicted. Dunkleosteus sat at the apex of one of the first complex marine predator hierarchies in the history of vertebrate life, a fish older than dinosaurs, older than trees, that had already solved the problem of building an unbeatable bite 350 million years before anything resembling a modern shark existed. Number 8. Basilosaurus. The year is 1834. You're Richard Harlan, an American physician and naturalist, and you have obtained enormous vertebrae recovered from Eocene-era rock in Clark County, Alabama, alongside teeth and additional skeletal fragments that had been surfacing from the region for years, mistaken by local landowners for the remains of a giant sea serpent or a fossilized biblical monster. Based on the material's scale and its serpentine vertebral proportions, you conclude you are looking at a previously unknown giant marine reptile, and you name it accordingly, Basilosaurus, king lizard. The name was wrong within 5 years, and the correction is one of the earliest and most instructive cases of self-correcting science in American paleontology. In 1839, British anatomist Richard Owen, who would go on to coin the term dinosaur, 3 years later, examined casts of Harlan's specimens and identified something Harlan had missed. The teeth showed a double-rooted structure, and the overall dental and skeletal anatomy matched mammalian, not reptilian, patterns far more closely. Owen concluded correctly that Basilosaurus was not a reptile at all. It was an early whale, one of the first fully aquatic cetaceans known to science, a genuinely ancient member of the same broad lineage that today includes blue whales and dolphins. The name never changed, a quirk of taxonomic rules that require the first validly published name to stand even after the classification underlying it is corrected, which is why one of history's most important early whales still carries a name that literally means king lizard, a permanent fossil of the mistake itself, preserved in the scientific record alongside the mistake's correction. What Basilosaurus represents scientifically is far more important than its misleading name. It lived approximately 34 to 40 million years ago, during the late Eocene, at a pivotal moment in whale evolution, when the lineage had already fully committed to life in open water, but had not yet evolved the body proportions of modern whales. Complete and near-complete skeletons recovered from Egypt's Wadi al-Hitan, Valley of the Whales, a UNESCO World Heritage Site that has yielded some of the best-preserved early whale fossils on Earth. Alongside the original Alabama material, show an animal reaching approximately 50 to 60 feet in length, but built along an extraordinarily elongated, almost eel-like body plan unlike any modern whale, with a proportionally small skull and vestigial hind limbs, tiny, functionally useless back legs, complete with fully formed knee and ankle joints. A direct physical remnant of the land-dwelling four-legged ancestors whales evolved from tens of millions of years earlier. Those hind limbs are among the most cited pieces of physical evidence for evolution in the modern fossil record, precisely because they serve no swimming function and cannot be otherwise explained, except as an inherited remnant of a walking ancestor. Stomach content analysis and bite-marked bone from smaller marine animals found in association with Basilosaurus specimens confirm it was an active apex predator of its era, hunting fish and smaller early whale species, including Dorodon, a related, smaller cetacean whose juveniles show bite damage matching Basilosaurus tooth spacing in multiple recovered specimens. Basilosaurus is not a monster in the sense the rest of this list uses the word. It is something arguably stranger, proof, preserved directly in bone, of the exact transitional moment when a land mammal's descendants had fully returned to the sea, but had not yet finished becoming what we would recognize as a whale. Number 9. Helicoprion. The year is 1899. You're Alexander Karpinski, a Russian geologist and paleontologist, examining a fossil recovered from Artinskian age limestone in the Ural Mountains. And it is unlike anything in the existing fossil record. A spiral of teeth, dozens of them, whorled into a tight, continuously curling ring, each tooth progressively larger than the last as the spiral winds outward. the whole structure clearly the product of a single animal's mouth, but arranged in a configuration that matches no known living creature. You name it Helicoprion, and then spend the rest of your career trying, and failing, to determine where on the animal's body this structure actually belonged. For more than a century after Karpinski's initial description, that single question, where does the tooth whorl go, remained genuinely unresolved, and the successive proposed answers form an unusually visible record of scientific reasoning correcting itself in public. Karpinski's own early reconstruction placed the spiral on the tip of the snout, curling forward like a circular saw blade mounted on the nose. Later, researchers relocated it to the tail. Others proposed it sat externally on the lower jaw, visible and exposed, functioning almost like a defensive weapon. Each reconstruction was published, illustrated, and circulated as the current best understanding, and each was eventually superseded as more complete material and better imaging technology became available. The resolution finally came in 2013, and it came from a piece of preserved cartilage that had been sitting in a museum drawer for years without anyone having the tools to properly interpret it. A team led by paleontologist Leif Tapanila at Idaho State University obtained a well-preserved Helicoprion specimen from Idaho that retained not just the tooth whorl but surrounding jaw cartilage, and subjected it to high-resolution CT scanning at Idaho National Laboratory, a technique that let researchers digitally reconstruct the internal structure of the fossil without physically damaging the specimen. The scans resolved the question definitively. The tooth whorl sat entirely within the lower jaw, curling backward into the throat, functioning as a continuously growing conveyor of cutting teeth, with older, smaller teeth pushed inward and retained as new, larger teeth erupted at the front, rather than being shed the way shark teeth typically are. Tapanila's team's reconstruction, published in the journal Biology Letters in 2013, also resolved a related long-standing classification confusion. Helicoprion was not a shark, despite a century of popular illustration depicting it as one. It belonged to a related but distinct group called eugenodontids, cartilaginous fish more closely allied with modern chimeras, sometimes called ghost sharks or ratfish, than with true sharks, a lineage that has left almost no other well-preserved fossil evidence, making Helicoprion's spiral jaw one of the only detailed windows into an entire branch of cartilaginous fish evolution that otherwise vanished almost without a trace roughly 225 million years ago at the end of the Permian period. Based on the corrected jaw reconstruction and comparison to related cartilaginous fish proportions, Helicoprion is now estimated at approximately 20 to 25 feet in length, an active predator using that spiral of teeth to snag and shred soft-bodied prey, most likely squid-like cephalopods, dragging them backward into the throat with each pass of the whorl. It lived through the Permian period, ending, along with the overwhelming majority of life on Earth, roughly 252 million years ago, in the Permian Triassic extinction event, the most severe mass extinction in the planet's history, one that killed off around 90% of all marine species and erased Helicoprion's entire evolutionary branch from the ocean permanently. Number 10. Pliosaurus funkei. The year is 2008. You're Jorn Hurum, a paleontologist at the Natural History Museum in Oslo, leading an excavation team on Svalbard, a remote Norwegian archipelago deep in the Arctic Circle, where permafrost and extreme cold have preserved marine fossils in exceptional condition. 2 years earlier, in 2006, a team member recovered an unusually large marine reptile vertebra from the site, what you are now excavating. In brutal Arctic field conditions, with a short working season each year before the ice returns, is the animal that vertebra belonged to. The excavation takes years. Hauling fossil material off a remote Arctic mountainside in short annual field seasons, and the media initially nicknames the animal Predator X before its formal scientific description is completed. In 2012, Hurum and colleagues Patrick Druckenmiller and Espen Knudsen formally described the specimen as a new species, Pliosaurus funkei, honoring Bjorn and May-Lis Funke, the amateur fossil hunters, whose earlier Svalbard discoveries had helped draw scientific attention to the site. Pliosaurus funkei belongs to the same broad family as Liopleurodon and Kronosaurus, short-necked plesiosaurs with massive skulls built for a crushing high-force bite, But the Svalbard material represents one of the most complete large pliosaur skeletons ever recovered, giving researchers an unusually solid evidence base rather than the fragmentary material that has complicated size estimates for other giant pliosaurs on this list. Based on that more complete skeleton, the formal 2012 description places Pliosaurus funkei at approximately 33 to 36 feet in length, with a skull measuring roughly 6.5 feet on its own, making it among the largest and best documented pliosaurs known to science, living during the late Jurassic, approximately 147 million years ago. A biomechanical bite force study conducted on the specimen, incorporating skull proportions and jaw musculature reconstruction, estimated a bite force in the range of 33,000 newtons, among the strongest calculated for any marine reptile in the fossil record, sufficient to inflict lethal damage on prey, many times its own body's structural tolerance. Associated fossil material recovered from the same Svalbard formation, part of what researchers now call the Slotsmoya member, a late Jurassic marine deposit, exceptionally rich in preserved reptile, remains due to the site's unusual burial and low oxygen preservation conditions, includes multiple additional plesiosaur and ichthyosaur specimens, some showing damage consistent with predation, giving paleontologists a rare, detailed picture of an entire ancient Arctic marine ecosystem rather than just an isolated predator. What makes the Svalbard find scientifically distinct from earlier giant pliosaur claims, including the historically inflated Liopleurodon figures and the plaster-augmented Kronosaurus mount, is precisely that completeness. Pliosaurus funkei's size estimate did not require scaling up from a fragment or filling gaps with informed guesswork. It came from a skeleton complete enough that the animal's true dimension simply did not need correcting after the fact. A rare case in the history of giant marine reptile discovery, where the first published number and the number that held up under decades of subsequent scrutiny turned out to be the same one: 10 animals. 10 separate branches of the fossil record, spanning nearly 350 million years, from armored Devonian fish with self-sharpening jaws to Arctic pliosaurs preserved in permafrost. Each one was once dismissed, in some form, as too large, too strange, too improbable to have actually existed, and each one is sitting in a museum drawer or a mounted display case right now, correctable, measurable, real. The plaster gets adjusted. The reconstructions get revised. The animals themselves were never the exaggeration. The water above them just kept the secret longer than anyone expected. Soot's coutures and turn on notifications if this is a conversation you want to continue. If this one reached something in you, leave a like and drop a comment with which of these 10 you'd least want to meet in open water. Every time I go back through these specimens, I think about how much of this evidence sat undisturbed in the ground for millions of years longer than humans have existed as a species, waiting on a pickaxe, a storm, a low tide, or a CT scanner sensitive enough to finally read what the bones had been saying the whole time.